Right, so today we have Ken Intriligator from San Diego, and he will tell about anomalies of 4D spin theories.
Yeah, thank you. Thank you very much for the invitation and for coming. I'll be talking about some paper with postdoc Daniel Brennan, and the work is very kind of heavily influenced by a paper from 5 years ago, 5 or 6 years ago, by Thomas and Clay. So I have to apologize to Thomas that this will be all very familiar stuff, but we'll kind of look at some extensions was the motivation. So just to give some general introduction, like kind of like the big picture is we can think of quantum field theory as some kind of machine where there's some UV theory that we start off with, and then there's the quantum field theory RG flow. And then there's some theory in the infrared. And we know from examples that there are all sorts of different possibilities that could come out in the infrared. And often different UV theories can lead to the same infrared theory. And this is dualities. And so it's interesting to try to constrain this relation between the UV and the IR. And so that's something that symmetries can help with. So let's see, the infrared theory might be unknown, and symmetries can help. We look at a theory with symmetries, and one way that they can help concretely was discussed by a Tuft, which is a Tuft anomaly matching. And the idea of a Tuft anomaly matching is that these are some, well, the way that a Tuft originally phrased it was that these are some obstructions to gauging global symmetries. So we'll have some global symmetries. And if we were to try to gauge it, there would be an obstruction. And then the idea is that that obstruction is independent of any continuous symmetry preserving deformation. And so anything that we can do that doesn't violate the symmetry that's continuous, these Tuft anomalies would have to stay constant. And in particular, they're constant along RG flows. So if we have some kind of symmetry here and we can compute the Tuft anomalies here, then they would have to match in the infrared. And so this gives some kind of constraint. I should say they're constant along the RG flows. And so one thing that can happen is as we go towards the infrared, the symmetry can just be spontaneously broken. And if the symmetry is spontaneously broken, then it seems that these Tuft anomalies, as far as we know, don't necessarily help that much. They can tell us interesting things about the infrared theory, but as far as I know, they can't be used to rule out spontaneous symmetry breaking. So one option is there might be spontaneous symmetry breaking, and usually that's okay with the anomaly matching. Maybe it says that there could be like some domain walls with some TQ of T on the domain wall and things like that. So there's still something to be learned from it, but but in general, it's not an obstruction. Another possibility is that the infrared theory might be just some kind of interacting conformal field theory. So interacting capless, it might be a free theory or a conformal field theory. And sometimes you can rule out the free possibility because you could show that every possible free field theory doesn't have anomalies that match the original UV anomalies. So this is something that sometimes can be ruled out. But if it's an interacting conformal field theory, then there are probably also still some constraints that could maybe rule out that scenario, but I don't really know of an example where that scenario has been ruled out by anomaly matching. So usually this thing is okay with anomaly matching. One thing that you can often rule out is symmetry preserving gapped. And in that case, sometimes you can rule that out by anomalies. This is just some kind of motivation, but I'll go into a little bit more detail about some of this. And so the kind of the big motivation for what we were looking at was to look for there can be new Hooft anomalies. In various different ways, and the particular so there's a variety. Sure. And the ones that I'll be especially discussing are the ones with. Our focus. These ones where SpinG and 4 dimensions. So I'll explain a little bit more what I mean about that. But that'll be the focus for the talk. Let's see. Yeah, so maybe maybe I'll just say some general things about Hooft anomalies. So the one way. So just to remind people, or if you haven't seen it before, to give some examples, in 4D. Theory, the original way that Hooft anomalies were seen was from looking at triangle diagrams, where we have a global flavor at each vertex. And so, for example, if we were looking at QCD, we could put SU and F left chiral current at each vertex. So there's an SUNF left, there's an SUNF right, there's baryon number. We could put whatever, we could compute at Hooft anomalies for all of them. So we could put any global symmetry at these vertices. And here I'll just talk about the particular case where it's SUNF left. So then we do compute this triangle diagram. So trace SU and left cubed. And one way to think about, nice way to think about this triangle diagram is we can turn on background fields for the global currents. And so we'll turn on background fields for the global currents. We can compute this thing, and we'll see that in some normalization, it's NC, just because we have the left-handed chiral fermions running around the loop, and there are NC of them. And so here we would say that there's an Hooft anomaly, which is NC, and whatever happens in the infrared, that NC has to be matched by something. And so one way that the NC could be matched, for instance, so this must be matched. In the infrared. And one way that it could be matched is by so if we have chiral symmetry breaking, then lift anomalies are matched by the pion nonlinear sigma model. And so because we'll have in this coset, so if we say this is G, this is H, so then the pions live in the coset. Which is like a SUNF, let's write it like F minus, right? And here, let me just say that I'm talking about the case where NF is 3 or bigger. So if this thing uses the cubic Casimir of the group, and so if it's SU2, we don't. That's a special case that we would have to discuss separately. So for SUNF big 3 or bigger, what happens is there's a Western term. Related to the fact that we can write down a 5 form on this coset with coefficient. Matches the anomaly. Okay, so that's one example of anomaly matching, and what you learned something that there's this was Witten term with coefficient NC, which Witten argued for in a classic paper from I think 1982 in several different ways. Stop me if there's any question. Yeah, the case SU2 is a special case. So in the case SU2, in the case of SU2, we'll have this G mod H is a 3-sphere, and so then we can't write down this Western-Witten term, and for the SU2, let's say for SU2 left global symmetry, we have, so maybe that's right here. So in mind that there's an SU and C gauge group, and an SU2 flavor symmetry. We have some chiral fermion psi, which has a 2-component spinor index, color index for SU and C, and a flavor index for SU and F. So it's like in the fundamental of these. And then there's also left, left right, it's trivial. There would also be the psi bar, which is in the anti-fundamental. Let's call it psi tilde.
I mean, and I think also too.
Yes, thanks. Yeah, thanks. Okay, so So under this SU, let's just call it SU2 left. So under SU2 left, there are NC doublets. And this actually gives another example of a 't Hooft anomaly, which is that if we tried to gauge this SU2, it wouldn't show that it would have an anomaly if the number of flavors is odd. So if this NC were odd, then this theory would have a 't Hooft anomaly for that SU2. And that's sort of like what we would get from this anomaly if we were to just naively continue down to, not really naively, but if we were to continue down to NF equals 2, we would say that this would be the analog of that anomaly. So again, the coefficient is NC, but for the case if NF equals 2, there's just a mod 2 matching. So if NF is bigger than 2, we have to match this coefficient NC, whereas if NF is 2, we just have to match if it's even or odd in the infrared. A nice way to think about the 't Hooft anomalies is by the description in terms of inflow. So with inflow, the idea is that we take, and this is also used in constructing the Wess-Witten term. The idea is that we could take our 4-dimensional space-time to be the boundary of some 5-dimensional manifold. So let's say this is like our M4. This is our N5. And then what we can do is we can encode the anomalies, the 't Hooft anomalies of this M4 in a topological quantum field theory that lives on this N5. And so this is just a trick to encode the 't Hooft anomalies, but we can think about that there's some TQFT topological quantum field theory in 5 dimensions that has some chiral edge modes here. So it's like the kind of thing that comes up often also in condensed matter systems, and that matches the anomaly. So the idea is that, or the way that it works is we say that there's some partition function on M4, which is a function of some gauge fields. And these are background gauge fields. Or global symmetries. Like in this example, they could be SU and F left background gauge fields. And then what happens is that the 't Hooft anomaly says that this thing isn't actually gauge invariant. So if this lambda is some gauge transformation parameter, what happens is that the partition function is like in a projective representation of the symmetry. So instead of being invariant, it's invariant up to a phase. I times some alpha, and this phase alpha depends on a mu and lambda. And so we would say that this is like, we can think about this as a quantum statement because when we have a Hilbert space, we just have projective representations of symmetries on the Hilbert space, because in the end we'll be taking the norm anyway to compute probabilities. And so this is allowed. So this is projective. That this alpha is non-trivial. And this alpha is the 't Hooft anomaly. And what happens is that we could write this alpha as the phase that we would get from some topological quantum field theory in the bulk. So, like for instance, in this case where we have this trace U at SU and F cubed, there would be some 5-dimensional Chern-Simons theory. And so the 5-dimensional Chern-Simons theory, if we do a gauge transformation on that, it'll reproduce this phase. And so we can have some picture in 5D where we have the H fields A mu on this side and A mu lambda on this side. And we get that phase from some path integral of some topological theory, which is like e to the 2 pi I times some omega 5 A in the bulk. And then this gives this phase difference that we have on the two different sides. And one thing that we can do with this now is we can, so here, this would be like if we were to extend this now and do the gauge transformation, we can think about it as coming from some integral of this over this N5 where we have some boundary conditions, A mu on one side and A mu lambda on the other side. And what we can do with this now is we could glue those two sides together if the gauge transformation is trivial. So if we have some kind of isometry and a trivial gauge transformation,
M4 or M5?
oh, sorry, thank you. M4. Yeah. And the trivial gauge transformation, what we can do is use that to glue the two ends together. And here I put in this isometry for some use that I want to use in a minute. So let's call this isometry phi. So phi might be some kind of symmetry of the 4 manifold, and then we also glue the ends together. And so in the end, what we'll get is some 5-dimensional space without boundary. And in this space, so we have, when I say we're gluing these two ends together, there's like a circle, and then we do some transformation by phi hat, and so we get some, so it's again M4. So this, let's call this now our N5, some phi hat, and this N5 is what's called the mapping torus, or a mapping torus. One thing that we can do with this mapping torus now is we say that the partition function of this M4 A mu has to be this mapping torus some phi form. So here, because I glued the two ends and they're gauge equivalent, these are both Z of A. So we get some identity like this.
You're assuming that lambda is non-trivial in the bulk of N5, but trivial on the boundaries.
Yeah. We could, yeah. That's right. So what we can conclude from this is that either this phase factor is 1, so that's one option, is that this phase is 1, or the second option is that this partition function is just 0. So those are the two different options. And in some cases, we can show that this phase is 1, and that this phase is, sorry, if the phase is not 1. And in some cases, we can just show that the phase is not 1, and so then we see that the partition function is just 0. And this argument was so this is kind of an old argument that was discussed in like in Whitten's paper on the Whitten anomaly, and this argument was also applied in some more recent papers by Clay Cordova and Kantaro Mori, where they ruled out some symmetry preserving gap phases with TQFTs. So one application, which is, I'll just kind of mention as an aside for the moment, is a few years ago, argued that have phase not equals to 1, and so then we would say that there's an 't Hooft anomaly. We can think about this as some 't Hooft anomaly that has to be matched. And they argued that the goal was to argue that various TQFTs, assuming unitarity, so we start off with some unitary theory. We RG flow to the infrared. We should have some infrared theory. One possibility for the infrared theory is a gapped theory in the infrared, which could be trivially gapped, or it might, more interestingly, it might be some TQFT. But sometimes you can argue that TQFTs, this is what they argued in various cases, that the TQFT has a partition function that's not 0. It's 1 in some units. And so if it's not 0, then that's a problem, because this anomaly says that the actual quantum field theory has a partition function which is 0. If a TQFT gives a partition function that's not 0, then that says that that can't be the infrared theory that this theory flows to. So it can't flow to a TQFT in the infrared. Okay, so that's some application of these mapping torus. Going back to the Whitten anomaly. please.
Thomas asked about lambda being non-trivial in the bulk. Is that related to the isometry? The isometry phi that you connect the two boundaries?
Yeah, so the isometry phi could be whatever we like. And the gauge transformation could be whatever we like. So we could just, the idea is we could just try to look at every possible mapping torus that we could possibly think of. And if we find a mapping torus where this phase is not trivial, then we would say that for that mapping torus, or for that case, the partition function has to be 0, and then this argument would say it couldn't be matched by a TQFT. Yeah, so we can just pick anything we like. But we just have to make sure that the two ends match up. Yeah, so just to, as an example of this, we can look at the Witten SU2 anomaly. And the argument that Witten had in his original paper was basically that if we were to look at the 4D Dirac operator as eigenvalues in plus or minus pairs, and then we wanted to find if we wanted to look at the what we get from the path integral. The path integral is like some square root of the determinant of this Dirac operator. And so to take the square root with these plus or minus pairs, one way to try to do it would be to just throw out the minus sign pairs and just take the square root by taking the product of the eigenvalues. So we could try to define square root. But the problem with this that Witten argued is that this doesn't work. Because we can do some gauge transformation. With some parameter that's it starts off like in an interval, and then we identify the two ends of the interval. This is basically like this circle of the mapping torus. And that, as we do that, what happens is if we look at these eigenvalues that have if we look at these eigenvalues and we try to keep, say, only the ones that are positive, what happens is that some of them cross, and there's an odd number of these crossings. And because there's an odd number of these crossings, what in the end you get is that this thing ends up basically giving a partition function that's 0. So it's the same 0 that we had here for the partition function. And the way that we can see the 0, but the way that we can see it in terms of this description is we look at so the mapping torus is just 4 times a circle. I said there could be like some semi-direct product and with some phi hat. And the phi hat, in this case, we could take it to be whatever we want. And so we could take phi hat to be -1 to the f. And if we take, and then basically what happens is that the number of crossings is the mod 2 of some 5-dimensional Dirac operator on this mapping torus. And the -1 to the F tells us that these fermions have periodic boundary conditions on the circle. So periodic boundary conditions on the circle are nice because then we can basically just look at the constant mode on the circle. And so then what happens is that this mod2 index of the 5D Dirac operator just ends up giving the mod2 index of the 4-dimensional Dirac operator. And we could take any configuration that we like. And so one configuration is we can look at an SU2 instanton. And if we look at the SU2 instanton, an index theorem tells us that there's one fermion zero mode. Well, so if we just had, here I'm looking at the case where there's a single SU2 flavor. Let's just say that there are, before in my example, I said that there were NC flavors because of this QCD example. So I could say that that NF is now NC, but that's kind of confusing. So let's just say that we have a single with one doublet.
One,
Or an odd number of doublets. Or let's just say odd number.
what do you mean, not Dirac flavors, you mean vial?
Yeah, an odd number of vial.
Maybe you imagine the flavors.
Yeah, in Whitten's argument, it was, in his original paper, he was thinking about it as a gauge symmetry. And then in the application for 't Hooft anomalies, I'm thinking about this as a flavor symmetry. But so for this, it doesn't really matter. So if we have an odd number of vial doublets, then the number of these fermion zero modes would just be the number of doublets. And then we see that if the number of doublets is odd, then that tells us that this phase that we can integrate over this mapping torus ends up being -1. So we get this e to the 2 pi I times the integral of something. Let's just still write it as if it were some phi form. And so this is what's now called the old Whitten anomaly. That's not a statement about Whitten's age, but just because there was a newer version of the Whitten anomaly. So this is the old Whitten anomaly. Okay, any question about that?
So does this argument with the -1 to the F show that the theory is bosonic? There is actually no Whitten anomaly? So is it important for the bulk theory to have -1 to the F somehow?
I don't think it's important. Yeah, I don't think it's important. So these
So a purely bosonic theory can have a Whitten anomaly?
I think so, yeah. So these discrete anomalies at least if there are no continuous 't Hooft anomalies, then if we have discrete 't Hooft anomalies only, then they're classified by cobordism groups. And there were some great papers from 10 years ago by Kapustin and Ryan Thorngren, especially about this kind of cobordism classification. And so in this case, the cobordism group is omega 5. So in the bosonic case, I think this Z2, this is a true statement, and that's the Oldwooden anomaly.
But let's not be too.
Oh, sorry.
I think the weight is spin.
Spin, yeah. I just realized I wanted to write the opposite. Yeah, so in the spin case, that's Z2, and then in the non-spin case, then it's actually a Z2 plus Z2. And so that I think this extra Z2 is the new Wooden anomaly.
Yeah, that's the W2, W3.
Yeah. So that's so.
I mean, that was nothing.
So there's an extra. Well, not the anomaly, but new when Wang within
They really didn't discover this.
anomaly.
They found an example, but it was understood long before.
Yeah, and
The fact that there is an anomaly was
yeah, it was in the Fried and
no, even long before Fried. I think it's just W2, W3.
yeah. So in fact, yeah. So that basically brings me to why I wanted to talk about.
But you're saying the Z2 Witten is present both in the spin and in the non-spin case.
I think it's probably only in spin case because it implies fermion-parity.
Well, that's what I was asking.
Yeah, and then actually the coefficient, I think for the coefficient group for SO is only a single Z2.
And it's W2, W3.
Yeah. I mean, we thought extra symmetries, of course.
Yeah.
Okay, so this was all probably much too long of an introduction, but I wanted to talk about these new kinds of 't Hooft anomalies with involving Stiefel-Whitney classes. So yeah, so this so I'll call this anomaly this thing. I just want to do my note make 2 pi I. So the anomaly, you can have an anomaly term which is like a half integral over some n5. It doesn't have to be the mapping torus. And let's say here there could be some coefficient that I'll call kappa tt. This is an example of a 5D gravitational anomaly. Which I think was first pointed out by Kapustin. And then he had another paper with Thorngren. About 10 years ago. And so this is an example of a 't Hooft anomaly that we can have if we put the theory on a non-spin manifold. So this W2 is this Stiefel-Whitney class, which is the obstruction to having a spin structure. W3 is some obstruction having spin C structure. And for 4-dimensional spaces, this W3 is 0. Oh, the T is just for tangent manifold, just as a reminder that this is like a gravitational anomaly. So this would be like if this coefficient kappa is odd, then I would say that this is a gravitational 't Hooft anomaly. It's a mod 2. So basically, this was TT. This thing ends up being an integer, and this whole thing will give a non-trivial phase if this anomic term is half integral. So then this will have this e to the I pi, and it'll be -1. And so this kappa tt is some integer, and if it's an odd integer, then we would say that there's a gravitational anomaly. So this kappa tt is a 't Hooft anomaly. And an example where that happens is all fermion electrodynamics. So in all fermion electrodynamics, we just have Maxwell theory. And so it looks like there are no fermions in the problem at all, but we have then line operators. We can have an electric line operator, a magnetic line operator, and a dionic line operator. And the usual case is where we pick one of those three to be a fermion, and then the other two are bosons. And in that case, we don't have this anomaly. But if we take all three of them to be fermions, then this kappa tt is odd. It's yeah. Okay, so that's and one possibility, one nice sort of canonical choice some M4 with the non-zero Stiefel-Whitney class of M4. So basically, maybe I'll write this as like this, where this is basically like, we can think about this as like a D derivative. And so when we go to the boundary, what we get is that this can be non-trivial if the boundary theory has some non-zero second Stiefel-Whitney class. And so a canonical choice for a boundary theory, which is our four-dimensional space-time with a Stiefel-Whitney class non-zero, is CP2. So we can imagine taking our 4D space-time to be CP2. In this case of all fermion electrodynamics, and CP2 was studied actually by my colleague John McGreevy and his students Shana Krevik and Brian Swingle, and they had some section of their paper where they wrote bad things happen on CP2. And so the bad things that happen on CP2 are related to the fact that this 't Hooft anomaly is non-zero if we look at this theory on CP2. So this is
What good things happen. There's nothing bad about it.
yeah. So it's actually at the time they weren't thinking about it as in a 't Hooft anomaly, and so they called it bad. But actually, 't Hooft anomalies are extremely good because then they tell you something that you could match if we tried to match things in the infrared. So, like for instance, in another example. So the Wen, Wang, and Lydon anomaly example was SU2 gauge theory with NF equals 1 while fermion in the 4D rep SU2. So you can think about this as like isospin 3/2. So the case of one vial fermion in the 2D rep of SU2 was Witten's original old SU2 anomaly. And so that would be like the I equals 1/2 case. So this is the I equals 3/2 case. And in this case, if we were to look at an SU2 instanton, SU2 gauge, the number of fermion zero modes the number of fermion zero modes is just like the index of the Dirac operator in that representation, which is just some quadratic index of the representation. And so we can work it out, and it's 10. And the fact that this is an even number tells us that this theory doesn't have the old Witten SU2 anomaly. And in fact, this theory is a theory that I studied a long time ago with Seiberg and Schenker, the supersymmetric version of this theory, and kind of interested in also in the non-supersymmetric version. But so the fact that this is 10 means that the theory is consistent. If this had been a global symmetry, you know, the old anomaly that I mentioned was the 5th anomaly, but if it were a gauge symmetry, then it would just say that the theory is inconsistent. But this theory is perfectly consistent, and but it has an anomaly. Just write the answer, which is 1/2 integral of. It has this anomaly that I wrote before. With coefficient, with an odd coefficient, and so it has the same 't Hooft anomaly as this all fermion electrodynamics. And in fact, Thomas and Clay and Daniel Brennan had some paper where they studied various deformations of theories, and by adding scalar fields, which is always fine, and which could be given a mass without violating any symmetry. And so you can kind of add it for free as far as anomalies are concerned, and show that you can go from this theory to all fermion electrodynamics, and that's consistent with the fact that they have the same 't Hooft anomaly. And this is an example of a theory which is where we have to say some extra words about putting the theory on CP2. So you need to use the fact that it has a spin SU2 gauge in this case for structure. And so the crucial thing about this theory is that -1 to the F, which gives fermions a minus sign, is the same as the SU2 gauge center symmetry. So the fact here that the fermions are in a have odd isospin means that if we do like a 2 pi gauge rotation, they'll pick up a minus sign. And also they're fermions, and so there's some correlation between the Z2 center of SU2 and the 2 pi rotation in space. And so this is an example of a generalized spin structure, which is allowed if all of the fermions all fermion gate dynamical matter in I equals autographs and bosonics is an I equals either representation. So like for instance, the gauge fields themselves are in the adjoint, and so that's I equals 1. So this is an example of a theory where there's a generalized spin structure, and the fact that -1 to the f is actually in the gauge group means that when we do the gauge symmetry, we're gauging -1 to the f, and so actually there are no fermions in the theory at the end of the day. If we look at gauge invariant operators, the infrared theory is the gauge invariant theory is actually bosonic. So in this case, the theory is actually bosonic, even though it was formulated originally with some non-gauge invariant variables that looked like they were fermions. Everything that's gauge invariant in the infrared is bosonic. And so we can put the theory on CP2, we can compute this and see that it's non-zero. And in fact, this thing is non-zero. Or a mapping torus, which is N5 is CP2 semi-direct I hat the circle. And this phi hat, we can pick phi hat to be whatever we like, but the phi hat that works is that phi hat is complex conjugation. Well, let's just say we take, so we think of CP2 as having coordinates Z1 and Z2, and then complex coordinates Z1 and Z2, then we complex conjugate them. So this is some kind of isometry of CP2, and this isometry, actually to get this thing to work, what we need is that the second Stiefel-Whitney class for the gauge fields has to be equal to the second Stiefel-Whitney class of the tangent manifold. And so here, because we're taking this to be non-trivial, we need some fluxes in the gauge fields. And at first this looks strange because SU2 has 0 Stiefel-Whitney class, but really what we want to do is we want to think about it as like an SO3, but not sum over the two different sign choices, but just restrict to one choice. So this is some non-zero flux. And this non-zero flux, when we do the complex conjugation, picks up a minus sign. And so to correct for that, what we need to do is put in, so this is, I'm repeating the argument from Wang, and Whitten. What we need to do is we need to combine phi hat with a Weil transformation. So there was some anyway, this is just some detail that we need to do. So we do complex conjugation, a Weyl transformation, we get this N5, and this N5 is, there's the Wu manifold. Old. There were some nice footnotes in a paper by Kantaro and Yuji and Lee about the funny fact that these names are kind of backwards. So one of them is SU3 times mod SU2, which is a 5 manifold. And the other one is this one. And these both have this be non-zero.
Oh, sorry. Is it SU2 or SO3?
Oh, sorry, I meant SO3. Yes. Yeah, thank you. They both have this W2 cup W3 over this N5 one. And so this is like a mapping torus that would tell us that that the partition function has to be 0 in this case. And so the fact that the partition function has to be 0 in this case means that there's a 't Hooft anomaly. What should I do about the time? I actually haven't even started talking about my paper. I was planning to talk about my paper as some generalization of Thomas and Clay's paper, and I haven't even talked about Thomas and Clay's paper. I mean, I could try to wrap it up relatively quickly, or I could just stop now, or whatever.
There is a pizza
Well,
готов.
we can at least wait until the pizza gets here, but it's not here yet.
Okay.
But yeah, it will probably get here in like 20, 25 minutes or so.
Okay.
Maybe that's a natural cutoff.
Okay. All right, I'll try to become more efficient now. So this is a case where it's a spin SU2 gauge symmetry. So in the talk title, I said SpinG for structure. This G could either be a gauge symmetry, in which case the theory is actually bosonic, or G could be a global symmetry. And so here I was talking about the example where G is the gauge symmetry. We can also take G to be a global symmetry. And so then -1 to the F is, for instance, in the center of some G global symmetry. Then we can do something similar to this picture, but the interpretation is different. The interpretation is that this is like the topological twist. N equals 2. And I don't mean that the theory is going to be topological. So in the topological twist of N equals 2, we take some N equals 2 theory, and we do a topological twist where we turn on background gauge fields for the G global symmetry. And what we can do with these background gauge fields is we can set W2 for those background gauge fields to be W2 of our 4D spacetime manifold N. And then if we do that, basically what happens is the background gauge fields make it as if those fermions are bosons. They're really not bosons, it's kind of just a trick. But it makes it as if there were bosons. And then in the topological twist, we do something else on top of that, where we write down some BRST charge using the supercharge. And the whole point of this topological twist is to twist the supercharge from being spin 1/2 to be spin 0, so you can rise the BRST charge. And then you get a topological theory. Here we don't need to do that, but the idea is that whenever whenever -1 to the f acts the same as the center, it acts the same as the center of the global symmetry, then we can still put the theory on a non-spin manifold. And this is what Thomas and Clay did in their paper. So we could look at, as an example, let's suppose that we have some G gauge theory. And F equals 2 adjoint fermions. So in other words, the number of Dirac fermions is 1, and we'll just write the Dirac fermions as Weil fermions.
If -1 to the f is not in the center of G, not in the center of the global or the gauge group, then can I say that the theory cannot be placed on a non-spin manifold?
That's right. That's right. Yeah. Yeah. So if you have if -1 to the f isn't so this is kind of like a loophole to the usual statement that you need a spin structure for fermions. And so if you don't have this loophole, then you just can't put the theory on CP2. So the idea is that if we do have this loophole where -1 to the f acts as something where we can kind of fix up the usual problem with fermions this way, this condition fixes up the usual problems that we would have with fermions on a non-spin manifold, then we can still study it on CP2 and try to get some new information. But yeah, if we don't have that loophole, then we're just out of luck, and we just don't consider CP2 in that case. Okay, so in this case, if there's NF equals 2 adjoint Weil fermions, there's a SU2 for any gauge group. There's an SU2 global symmetry. And the center has -1 to the f on all of our dynamical fields. So for instance, the gauge fields are invariant under this global symmetry, and they're bosons, and so the center acts trivially on the gauge fields, and the fermions are in the doublet of that, and so they pick up a minus sign under the center of this SU2 global symmetry, and they also have -1 to the f, it's -1. And so this is a theory which has a spin SU2 global theory. So we can put it on CP2. And look for new anomalies. And what Clay and Thomas did many years ago. Time flies. What they did many years ago was they argued for an anomaly where the anomaly theory A is 1/2 the integral over n5 we could write it this way. They argue for an ancestral anomaly like this, where this B is the background two-form H field or the Z2 one-form center symmetry, global symmetry. And so maybe I should explain a little bit about that. So, and here I'm saying this Z2 is because it was for SU2. The gauge group is SU2. So if the gauge group is SU2, then because everything is in the adjoint, the so in general, pure Yang-Mills theory can have a one-form global symmetry that's the center of the gauge group. So so if the gauge group is SU2, because there's a Z2 center symmetry, pure Yang-Mills has a Z2 one-form symmetry. And that Z2 one-form symmetry would be broken if we put in matter fields, like for instance for SU2 would be broken if we put in matter fields that were transformed non-trivially under the center. In other words, in half integral isospin representations, but here these are in the adjoint, and so they transform trivially under the center. So we still have the Z2 one-form center symmetry. We can couple it to a background field B2, and then the anomaly that they wrote down was this anomaly. And this anomaly was, they argued for by a reinterpretation of something that happens in the Donaldson-Whitten partition function. Topological quantum field theory. And this is an effect which I think was first pointed out by Donaldson, that if you look at the moduli space of instantons, then because of some effect with the orientation of this moduli space of instantons, the partition function can pick up a minus sign where Z can go into minus Z. So basically there are the pizzas. Okay, that's the cutoff. Yeah, so basically, sorry about this, but so maybe I'll just say what
5 minutes, right?
yeah, maybe I'll just take 5 minutes to say what we actually did. So what we actually did was there was a nice calculation in the Wang-Whitten paper where so if we call in general the coefficient of this anomaly kappa, then in their case what happened was that this kappa was half times the number, half of the index of the 4D Dirac operator using this mapping torus, which was CP2 half of the index of the Dirac operator on CP2 with some fluxes. So the reason why I was reviewing this whole thing with the mapping torus was because this is one of the ways that we actually computed these anomalies, was by looking at this mapping torus construction. And with the mapping torus construction, what happens is that in some cases you can very easily calculate this coefficient kappa just by writing it in terms of the index of the 4D Dirac operator on CP2 with some appropriate fluxes. And so this is a very straightforward thing to calculate. So in terms of like this Donaldson-Whitten partition function, you know, Whitten had some arguments to reproduce this minus sign from the topological quantum field theory. This was some supporting evidence that the topological Q of T was giving the right partition function, and that was some. In the end, it also, you know, was something that could be thought of as some. The fact that the partition, when you write the partition function as a path integral, it's like the Fujikawa kind of method of seeing an anomaly. You see that the fermions in the integration measure pick up a minus sign, but in that usually the fermions in the integration measure involve like some product over infinite number of, you know, over all the different fermion modes. But here it just reduces down to the 0 modes, and so you can just write it in terms of the index of the Dirac operator. So this is something kind of straightforward, and then using this, we computed this coefficient kappa for a bunch of different examples, like different choices of gauge groups here with adjoint matters and other different examples. And then we tried, when it was non-zero, we tried to look at, like in this case, with 2 flavors, one possibility is that the infrared theory is a bunch of copies of the CP1 nonlinear sigma model. And so then we tried to look at the matching with the nonlinear sigma model, and we find some possible interesting questions for future study that I'm still kind of interested in. But yeah, so basically the thing that I'm skipping is kind of the details of how we could compute this kappa from this index of the Dirac operator from this mapping torus construction. And in the end, you get just some very simple formula for this kappa, where if I were to go through the different examples, it's kind of like, yeah, like for instance, just to write a concrete formula. So there's some formula that you get like this from the index of the Dirac operator, where, so the index of the Dirac operator, you know, you write this A hat, this A roof genus. And so since it's the 4D Dirac operator, we look for the 4-form term in here. And so there's one piece that comes from the second term class, and that's going to give this piece if we just look in some U1 subgroup. And then there's a term from here, which for CP2 gives us this factor. And these would be like the charges under some U1 subgroup. So like for instance, in the Wen-Wang-Whitten example, since they have this I equals 3/2 representation, under this U1 subgroup, Qi could be 3/2, 1/2. This is just like the charges of the fermion matter under this U1 subgroup. And so we just plug that into this formula, and we'll see that, well, maybe I need an extra factor of 1/2. So this is the index. The index of the Dirac operator is this thing in parentheses, and then this kappa is like 1/2 of the index of the Dirac operator. So basically, we'll see that these ones cancel. These things will give 9/4 minus 1/4, And so that's 2, and then we take a half, we'll get 1. Okay, so basically what happens is that we'll get, if I did it right, this kappa should be 1 in this case. I might need an extra factor of a half. And it's completely analogous for the other examples. So we just have to look at some set of charges that activate both the mapping torus flux that we need to make the theory well defined on CP2, and also this B field. So in the case where there's a B field, this B field will contribute to our choice of charges here. And then with that, we can compute the kappa, and we can reproduce, for instance, like this Hittov's anomaly. Sorry to go 20 minutes over.
In a general setup, is there any indication of what isometry you could pick to get something on circulation? Everything seems.
Yeah, so in the end, like in the end, we want something that's like this. So one clue in this case was we could just try to write down what are the things that are sensitive to those cobordism classes. So here, like this omega-5 is measured by something which is like a W2, W3. And then those W2, W3s were basically only the Wu manifold or this Dold manifold. And so even though it, like in the Wen Wang Witten paper, it kind of looked like out of the blue that they took this chart complex conjugation as the choice of isometry for when they glued the 2 ends together of the circle. It actually really had to be that, because we needed to get a mapping torus which is non-trivial, and it was only one or the other of those. And so the fact that there was like this mapping torus, which was this Dold one, which you get from that, was kind of a clue to the right one to pick. Yeah, thanks. Yeah. So for example, if in the case where we take G to be G with 2 adjoints, what we find, for instance, is that this cap is not 0 for instance, SU 2 NC with NC odd. So like for SU2, and which was the original example where it was related to this -1 for the Donaldson-Witten partition function. But in general, the same thing. Yeah, so another way to package this would be as a calculation of these minus signs that the Donaldson-Witten TQ of T could pick up. I don't know if from this point of view it was computed for SU6, but this would be some calculation that says, for SU6 it has the same minus sign, whereas for SU4 it wouldn't have a minus sign. Yeah, and we looked at a bunch of different examples, but this was like also SO groups with fundamentals and things like that. The cases to look at for this kind of anomaly is where there's a center symmetry that includes a Z2. Like this anomaly is always a Z2 anomaly, and so we need a center symmetry that includes a Z2. And yeah, so basically, like for SU6, there was a Z6 center symmetry. So it's kind of like an anomaly in the Z2 subgroup of that Z6.
Actually, I was just wondering, so you compute so many examples. So in the case when the anomalies agree, can you find some deformation that cannot defend gauge group or like different theories with the same anomaly, like, or maybe that
Yeah,
other
we,
anomalies that distinguish them.
yeah, we didn't look for something like that. That would be nice if there were like, I mean, I guess, yeah, the simplest, well, so another argument for this kind of anomaly is the argument that also was in another paper by Thomas and Clay, together with Daniel Brennan on fractionalization, where you add, like for instance, adjoints of the gauge group and you Higgs down to the Cartan, and then you relate it to the anomaly for the one form, the mixed Etops anomaly for the one form symmetries of pure Maxwell theory. And so I think all of these examples could be deformed to that case, where you could see them as connecting to just pure Maxwell type anomalies. But
Can I use an
we didn't.
to say something about like the infraphase of those like different gauge groups, different, yeah.
Yeah. So my impression is that so like for instance, this theory with the two adjoints has a bunch of different Etops anomalies besides this one.
Yeah.
And so the other Etops anomalies tell you some things, like they tell you that there's a discrete chiral symmetry, which is the unbroken subgroup of the AVJ anomaly. So those anomalies tell you that thing can't be matched by a symmetry preserving TQFT, and so for instance, like those ones could be spontaneously broken if we go to the sigma model possibility. But yeah, we looked a little bit at trying to apply these anomalies by like looking at this case with two adjoints, where the natural possibility would be a bunch of copies of the CP1 sigma model. And yeah, we kind of still trying to think about some aspects of that, but
Can like some of them flow to a same phase, like can you sort of discover some duality based on, or conjecture some duality based on the anomaly?
yeah, that would be nice. I think so. These anomalies seem kind of weaker than like the Etops anomalies for continuous symmetry sometimes are very non-trivial to match, and then as you know, then it can kind of motivate some very interesting non-trivial dualities. Here they're, I think, kind of simpler to match, and so it's maybe less constraining, but I think it's something I haven't really thought enough about. So I always hope to get more mileage from anomalies. Yeah.
Other questions? Okay, so let's thank Ken again.